Hello, I am MD Burhanuddin. I am a recent graduate in Material Science and Engineering from the University of Rajshahi, Bangladesh. In this presentation, I will share the fundamental concept of reciprocal lattice, Brillouin zone, and band structure. So let's start. So as you can see in the presentation, first slide, just the introduction. So okay, fine. This is the outline. I will explain the fundamental concept of reciprocal lattice with the help of Young's double slit experiment. Then I will discuss reciprocal lattice. After that, I will discuss Brillouin zone and band structure. I mean the EK diagram of solid. So first of all, Young's double slit experiment. I will not go to the full theoretical derivation or anything else. I will just show you the fundamental concept. So this is the equation y equal x lambda by d. Here d is the distance between the slits and lambda is the wavelength used to perform the experiment, and here I just put some circle where this circle represents the higher intensity is higher circle and lower intensity or lower spot is lower circle. So these are the spots. Okay, fine. And the distance between the spots is y. The first or the middle spot is highly intense. After that, the intensity is decreasing gradually. But we have to consider that the intensity may decrease, but the distance between the spots remain constants. So and these are the double slit experiments performed by scientist Young. Okay. Now if we decrease the distance, so first of all, as you can see, if we remove the distance between the photographic plate and the double slit, which is x and lambda, so our relation between the slit distance and the spot distance is inverse. So y is inversely proportional with t. So if we decrease the distance, our spot distance will increase, and if we increase the distance, our spot distance between the two spots will also decrease. Here you can see. So what if we consider another slit, just not consider double slit, we will consider triple slit. So in this case we will find there is two, not one, two highly intense spot. After that we will find the intensity gradually decreased, and interestingly this time also the distance between the spots will remain constant. Okay. So what if we consider this experiment into atom, like these are the one dimensional atom, I am considering one dimensional atom, these are the atom, and the spacing between the atoms we consider it the slit. As you can see, these are the slit, these are the atom, this tiny distance is slit, this is still slit, and so we will also find a regular one dimensional spot. After that we will find it gradually decrease spot, so we will not consider that. So if we decrease the distance or reduce the distance between the atoms, we will find the spot with higher spot distance, as you can see. And also here, if we increase the distance between the atom or increase the slit distance, so we will also find the lower spacing between the spots. So this is our the fundamental concept. So we will go to the reciprocal lattice. So instead of one dimension, what if we consider two dimensional lattice? So if we consider two-dimensional lattice, we will also find two-dimensional spots. These are the reciprocal lattice. So if we consider again the three-dimensional, we will also find three-dimensional lattice. These are also the reciprocal lattice. So black one is reciprocal lattice and the blue one is real lattice, as you can see. We just consider it for cubic system. We can consider it in hexagonal, trigonal or any other system, but that will bring us complexity. So for simplicity we consider cubic system. So from the Young slit experiment, if the distance between the atoms is closer, we will find bigger reciprocal lattice, and if we consider or if we take higher distance between the atoms, we will find lower reciprocal lattice. So these are the concept. So now go to the next session is Brillouin zone. So we consider this two-dimensional reciprocal lattice. So two-dimensional reciprocal lattice, and if we consider just a single point, anywhere of the point, if we consider single point, then just consider the nearest atoms. So if we consider this atom, so the nearest atom is this one, this one, this one and this one. So we have to just consider the nearest atom and select the bisector. So this one and this one, the bisector is this, and this one and this one, the bisector is this, like this one and the another one. So first nearest atom, the enclosed area is first Brillouin zone. Here you can see this is the first Brillouin zone. And if we consider the second nearest atom, we will get the enclosed area is second Brillouin zone. Sorry, the color is this is my mistake. This is green color, so I think this would be the yellow color, second Brillouin zone. And the third Brillouin zone is mentioned here. The third nearest atom is third Brillouin zone. So interestingly, if we fold the third Brillouin zone, we will get second Brillouin zone. Just consider it. And if we fold second Brillouin zone, we will get first Brillouin zone. So first Brillouin zone can represent all the crystal atoms. So here is the interesting thing: why do we need reciprocal lattice and Brillouin zone? Because in our real lattice there is a abundant amount of atoms in the crystal, so we cannot consider the whole crystal. So to do the simplicity work, we consider a reciprocal lattice, because each point of reciprocal lattice represents the whole set of parallel planes. So in this case we consider Brillouin zone, and specifically first Brillouin zone. Okay, as you can see, and this is the first Brillouin zone. I can show you more specifically. As you can see, this is the Brillouin zone. This is our real lattice and this is our Brillouin zone. Okay. So why Brillouin zone and band structure look like this? This is our three-dimensional Earth map, and if we plot in 2D, so this is our world map in 2 dimensions. So like the like our world map, so we can consider the reciprocal lattice Brillouin zone into the band structure. So in the band structure reciprocal lattice, we first consider this point. This is the origin of the Brillouin zone, and this can be termed as gamma point. This is 0 0 0 gamma point, and sorry, this is the gamma point, and these are the Brillouin zone, and the corner of the Brillouin zone is rhombohedral point. R is 1 1 1, M is M, here is the M is 1 1 0, and this is X is 1 0 0. So electron moves from one plane to one plane, and how electron can move in the lattice, we can predict this by the band structure. As you can see, this is the red line is Fermi level, and upper the upper band is conduction band and the lower band is valence band. So in the valence band we can see the level of band is, so the band is from X to R, like travel this path and down to the M to gamma to R again. So there is a limitation in band structure calculation by Castep. So I as you can see, I calculated this by Castep code embedded in Materials Studio software. But if we can consider it VASP, quantum espresso or Win2K, we can get the individual band by created by the individual atoms orbitals. So this is our limitation by calculated in Castep. So we cannot identify which band is responsible for this valence band. Okay, so this is our band, and this is direct band gap R to R. So this is direct band gap. If we get the R to M or R to X, this is indirect band gap. So this is our direct band gap materials, and very narrow band gap, I must say. Okay, the K points here tell us that this is in reciprocal space. As you can see, X R M G R G, sorry, it is gamma M G R. This is reciprocal space. Okay. One more thing I need to explain, that is if the valence band near to the Fermi level, we can consider it p type material, and if the conduction band near to the Fermi level, we can consider it as n type material. So in our case, the thallium germanium chloride 3 is p type material. We calculated it by Pardue-Bourke-Anzarov function. So this is PBE with generalized gradient approximation, GGA PBE. Okay, so this is our band structure. That's all for now. Thank you for being with me.